Welcome back. This is part 5 and the last part of chemical equilibrium. In part 1, 2 and 3 I addressed all the content, knowledge and understanding you need of this topic. In part 4 I looked at multiple choice typical exam questions. So now I'm going to look at longer questions and we're going to do 3 longer questions, and you are welcome to pause the video if you are looking at a video and not a live recording, and first try the questions yourself and then look at the answers and my explanations if the way you presented your answer would have been the same. Alright, so let us then jump into, I've got a question here which is relating to chemical equilibrium. One of the ways that you can easily identify a question that relates to chemical equilibrium is you will see the words equilibrium, you will see things like reversible reaction, you will see a reaction with the double arrows, and then you can know that you are most probably busy with this type of question, which is good then that you can know where you are more or less in your paper. All right. If we look at this question, it says here, the following equation represents a reversible reaction that has reached equilibrium at 470 degrees Celsius in a closed container. That's all the things that needs to be there for equilibrium to be able to reach, is we need to be in a closed system. Right, then I look at my equation that they've given me, and when I look at this equation I see that on the left hand side I have 2 gas particles or compounds that's going to react with one another, and then 2 moles of NH3 will form as a product. So that's my reactions, reactants and products. Then just for myself, I like to always now count my number of moles of gas. So on this side I see I have 4 gas particles that's reacting, the 1 plus 3, and on that side it's 2. So because those numbers is not equal now, I know that pressure changes will have an influence. Also concentration changes will have an influence, and also temperature changes I can know that will have also influence on this chemical equilibrium situation. All right, they say here a change was made to the NH3 in the mixture at T2. So something happened with the NH3, okay, at T2. A graph showing the effect of the change is drawn below. All right, so if I look at my graph, something happened at this time. I can see there's a sharp rise in amount, the numbers of moles of gas of the NH3. And then I can see what happened is that the amount of H2 increased afterwards, as well as the amount of N2 increased. And then I can see after that sharp change, the amount of NH3 decreased. So I know then that the reverse reaction was favored. I don't even know yet what is the question. I'm just kind of using what was given to me to see that because there's an increase in the number of moles of H2 and N2, it means that the reverse reaction was favored after this change was made to the NH3. All right, then they ask me in 10.1, they ask me what is the meaning of the horizontal lines between T1 and T2. So here I can see that the amount of gas remains constant. So that is one possible answer that you could have given, as that the amount of gas remains the same. You could also have said that the concentration of the gases remained constant, or you could have said that there is chemical equilibrium between T1 and T2, and the reason is exactly that these concentrations do not change. All right, so any one of those 3 would have been accepted. In 10.2, they say, state the change that was made to the NH3 at this time T2. So the type of change here will be one of you can either look at temperature or concentration change or a number of moles, that's the same thing, number of moles, or mass, it doesn't matter, but in this case we look at the amount of gas in moles, so it's number of moles, or the other one that we can look at is pressure, is another one that we can look at. So one of those changes was made there at T2. Now, only the NH3, the amount of NH3 sharply rise at that moment. So clearly what I did here is the amount of ammonia was increased. So you could have written down at 10.2, you could have said the amount of NH3 ammonia increased. So I added NH3 in there, in that closed container. Okay. You could have also said the concentration, I'm just using the abbreviation there, of NH3 increased. Just use the words when you write your answer. It would also have been accepted, concentration, or you could just have said NH3 was added. Any one of those three answers explains what happened there, that the number of moles of gas just increased. All right, so that is possible answers that would have been accepted. 10.3, they ask now, explain how this change mentioned in 10.2 affected the concentration of the H2 and N2 gases as shown in the graph. So I can see it raised, the amount raised, and thus the concentration also raised. Okay, so in your explanation, this now, when you get to this explanation, when there was a factor that disturbed, because at this time T2, the equilibrium was disturbed. The moment when you see there's a disturbance, then you know you need to think of Le Chatelier, and normally this is a 3 to 4 mark question. All right, so first of all, mention the disturbing factor. So for 10.3, I would say the concentration of the NH3 was increased. Okay, so that concentration was increased. Right, so what will happen now? According to Le Chatelier, the system will react to decrease the concentration of the NH3. How will that happen? It will favor the reverse reaction. All right, the reaction whereby this excess amount of NH3 now will favor the reaction to the reverse, and more of the N2 and H2 will form, and that's exactly what we see here in our graphs. Okay, so the reverse is favored, and look carefully, you have to explain what will happen to the concentration of the H2 and N2. So now I say the concentration of the H2 and the concentration of the N2 will thus increase due to that reaction being favored. All right, so that is 10.3. Refer to the disturbing factor, state what Le Chatelier will say, identify which reaction will be favored, and then make your final conclusion in terms of your question. All right, I hope that helps you a lot. Okay, now if we go to the next part, it says here 1.5 moles of N2 and 2 moles of H2 were injected. So that's what I started with. And here's an important part, into a volume of 0.5 cubic decimeter in this closed vessel. So now I know what is the volume of this vessel. And then equilibrium was reached at 470 degrees. When equilibrium was reached, then I had, and let me go to this now, new color, then I found that there was 1 mole of NH3 in the container. So that is after some of this reacted and formed NH3, this is the number of moles that was there present after equilibrium was reached. Okay, and now my question is, first of all, calculate the Kc value and show all your calculations. Okay, so you have to calculate the Kc value for this question. Now when you get this, it is very good if you can draw up a table like this. I'm sure your teacher have practiced this in class with you, and let's go through this again. All right, so I write down my two reactants. So those are reactants. Let's make them yellow like I did here there in the question. And there is my product. I use my balanced equation to then find the ratio in which they will react. So you can see there is the 1 to 3 to 2. Okay, so that there is my ratio. I find that directly from my balanced equation. Now I look at, did they give me anything with what I started? I have started with 1,5 moles of the N2. So here I can put in 1,5. And I've started with 2 moles of H2. And you will agree that I started with 0. Nothing was there present of the ammonia when this reaction started. So this is before equilibrium was reached. Now, some of this moles will be used up, to use that terminology, and it will now form NH3. So the number of moles of NH3 is going to increase. The number of moles of these reactants is going to decrease. There's going to be a change, and this change is the key for me when I work with doing Kc calculations using the table. That change is where I want to be, and that links the number of moles at equilibrium with the number of moles before equilibrium. All right. Then they said to me here in the paper that 1 mole of ammonia was present when equilibrium was reached. So at equilibrium, I had 1 mole. That was given to me. So what is the change now when I look only at this part? I started with 0, and I ended up with 1 at equilibrium, so the change is 1. All right, so I have identified that first one there that I really need. Now I can figure out the change using my balanced equation. Okay, so if I use my balanced equation, then I see that that 2 moles will give me, 1 mole will give me 2 moles of this. You can see it's half. So if I have any value here, I just divide by 2, then I get this value here. Okay, so if I have a value of 1 here, I divide it by 2, the change here will be 0,5. And now I know how much N2 was used to produce 1 mole of NH3. Okay, now I have a little trick here. Once I have a value of 1, then it's easy to know 1 to 3, I just multiply by 3 to know what will be the number of moles of H2. So 0,5 multiplied by 3, because this is now in a ratio 1 to 3, so then this will be 1,5. Right, so that is, these were used up, these 2, and then it formed 1 mole there. According to my balanced equation, I can work those ratios out. And that one I got from this value where I subtracted the 1 from the 0. Okay, now I can know what will be the number of moles that is left over at equilibrium. So I started with 1,5. I've used up 0,5 moles, so there's exactly 1 mole left at equilibrium of the N2. I started with 2 moles of hydrogen, and I used up 1,5, so there's 0,5 moles left at equilibrium. Now I like to here at the bottom, just for a reminder, state the volume of the vessel, and it was given as 0.5. All right, now I want to calculate the concentration at equilibrium. Why do I need the concentration at equilibrium? Because if I have the concentration of my reactants and I have the concentration of my products, I can write down my Kc equation and I can calculate. The question was calculate the equilibrium constant, the Kc value. All right, now to get the concentration, the equation of concentration is number of moles divided by the volume. All right, so I take my number of moles at equilibrium divided by the volume, 1 divided by 0.5, that gives me a value of 2. 0.5 divided by a volume of 0.5, according to this equation, will give me 1, and 1 divided by 0.5 again is going to give me 2. Now I have my concentrations at equilibrium. And that is the values I'm going to use in my Kc expression, in my Kc formula. All right, now I need to write down my Kc formula. To be able to write down my Kc formula, I go to products. There's my products going to the top, and that coefficient will be to that power, it will be given. So I will have my concentration NH3 will be to the power 2 because it's got a coefficient of 2. That is the product. And then my reactants, the reactants is N2, and that is to the power 1 because there's a 1 in front. And that I will multiply with the concentration of my H2, which will be to the power 3 because there is a coefficient of 3 there. And there is an equation now to be able to calculate the Kc value. Now I just substitute my equilibrium concentrations. So the NH3 concentration is 2, so I will have 2 to the power 2, and then my N2 will be 2 to the power 1 multiplied by 1 to the power 3, because that is my H2. Okay, and that's going to give me an answer then of exactly 2. There is my Kc value that I have calculated. And I've shown all my calculations, and for this you will get full marks, most probably about 6 marks at least. So you must be able to, I will really strongly advise that you work with a table. It makes your life really easy. And work from what is the number of moles at equilibrium, what is the number of moles initially, find that, because all the missing information can then be derived. Then you use your formula to calculate the concentration at equilibrium. All right, and then it's just substitution from there on. Now in the next question, 10.5, they ask you, the temperature is now raised to 800, from 470 to 800. And now they ask you, how will the Kc value be affected if the temperature increases from 470 to 800 degrees? And you only write down increase, decrease, or remains the same. All right. Now, the only thing that can change the Kc value is a change in temperature. So I know it's going to change. It's not going to stay the same. So that option is out. My second thing that I see here is it's exothermic to the right. So my forward reaction is exothermic. So what did I do? I increased the temperature. If I increase the temperature, the reaction or the system will oppose this change by trying to decrease the temperature, by favoring the endothermic reaction. And the endothermic reaction will be the reverse reaction, which will be favored. Right? Now, if the reverse reaction is favored, then this concentrations increase and that concentration decrease. Okay? So if that value decrease and this value increase, then my Kc value will decrease. Right? So my answer here at this question will then be, how will the Kc value be affected? It will decrease. Right? And now they ask you, explain your answer. And there, I will now put that nicely into words because that is my explanation. The disturbing factor is the increase in temperature. The endothermic reaction or the reverse reaction will be favored and the Kc value will increase. Right, so that was question 10. I hope that is quite clear, and let us move to another question. Okay, the next one I want to do, and you will see I'm focusing also a lot on graphs because the national moderator said last year that learners struggles with interpretation of graphs, and that is one of the reasons we pay a lot of attention in this year to address this problem. Okay, question 9. A fertilizer company produces ammonia on a large scale at a temperature of 450 degrees. The balance equation is given as below. It's the same equation as what we had earlier, so we know this one now, the production of ammonia. Okay. Now, to meet an increased demand for fertilizer, the management of the company instructs the engineer to make the necessary adjustments to increase the yield of ammonia. So this is what they want to do. They want to increase the yield of ammonia. So if I want to increase the yield, I need to favor the forward reaction. Then I will get a higher yield or a higher concentration of ammonia there. If I can increase the yield of ammonia, it must be done by forward, that the forward reaction must be favored. Whatever I do, that forward reaction must be favored. In a trial run, on a small scale in a laboratory, the engineer now makes adjustments to temperature, pressure, and concentration. So those are the three that he changes at T1, T2 and T3. We don't know when what, but here it is given. Okay, the graphs is now obtained. And this is an important one for you to understand. Now they ask, identify the changes made to the equilibrium mixture at the following times. T1, let's have a look at T1. At T1, at that time, we see there is no change in the amounts, the concentration of the NH3. No change in that and in the H2. So that one and the H2, the concentration stayed the same. But suddenly the concentration of the N2 increases. So yes, I have added N2 to the container. So I've increased the concentration of the N2. So that one deals with concentration. I'm looking at concentration, and at T1, the concentration of the N2 was increased. All right. What happens at T2? Let's look here. At T2, I see the concentration of N2, the concentration of H2, and the concentration of NH3 was increased. Now, the way I can do that is by increasing the pressure by decreasing the volume. If I make the container smaller, then immediately all of them is at a higher concentration. All right. So this one here in question 9.1.2 then deals with that the fact that the pressure on the system was increased. P was increased. The pressure was increased. All right. Now let's look at T3. Now at T3 I see there's no sudden change to any of the concentrations. So that means now that there was no pressure change, there was no concentration change. So it must be a temperature change. Let us now just see what was the change in temperature. Now if I look at this, I can see that the NH3, the concentration of the NH3 increased. No, sorry, the dotted line, sorry, is the H2. So the H2 concentration increased. That one there is the N2, so the concentration of the N2 increased. You can see it goes up. And this striped line is the concentration of the NH3. So the concentration of the NH3, that one decreased. So clearly the reverse reaction was favored. So the reverse reaction, if I look there, will be endothermic, because that delta H smaller than 0 tells me the forward reaction is exothermic. So if the reverse reaction was favored, it means the endothermic reaction was favored. How do I favor the endothermic reaction? By increasing the temperature. So here temperature was increased. You have to practice this. It sounds easy when I'm doing it, but you have to work with this and practice this and get to know this graph. Okay. 9.2, they ask you, at which of the above times did the change made to the reaction mixture lead to a higher yield of ammonia? Okay, so if I look at my ammonia, here is my concentration of ammonia. At T1, the concentration increased. So I'm happy with that. At T2, the concentration of the ammonia further increased. But at T3, the concentration of the ammonia, because it's concentration on this action, the concentration decreased because I can see the line is going lower. So where was the increase? At T1 and T2. All right? And now, you will almost always get this question now. It's a Casey question. They say the engineer now injects 5 moles of N2 and 5 moles of H2 into a 5 cubic decimeter sealed container. So there is my initial number of moles. There is my volume of my container. Equilibrium is reached, and upon analysis of the equilibrium mixture, he finds that the mass of NH3 is 20.4 grams. Now they ask you to calculate the value of equilibrium, of the equilibrium constant. Now again, I'm going to go to my table where I want my molar ratio, I want my initial moles, I want my change in moles, I want my moles at equilibrium, and then I want my concentration at equilibrium. Can you see, nowhere in this table is any indication of mass. But I know with this formula, I can convert that mass at equilibrium to number of moles at equilibrium. Upon equilibrium, he finds that the mass was that. So I can easily convert that then to a certain number of moles. So let's do that. Number of moles for the NH3 is then mass of the NH3 divided by the molar mass. And that is 20.4 divided by, and the molar mass, I use my periodic table. N is 14, H is 1, 3 of them. It gives me a total of 17 grams per mole. And this works out at 1.2 mole. All right, so there I have my number of moles of NH3 at equilibrium, 1.2. So now I can go to my table and I can say at equilibrium, I there had 1.2 moles. So that comes directly from that calculation. That was the number of moles present at equilibrium. All right. Now at equilibrium, it didn't say anything that I started with some ammonia, so that would be 0. Then also the change must be 1.2 because I started with 0, 1.2 moles forms, and then 1.2 moles will be there at equilibrium. Now let's fill in our ratio. Looking at my balanced equation, I can then indicate that my ratio was 1, 2, 3 to 2. Okay, so that I I now do have. Now I can say, for this to form, 1,2 moles to form, I can go to my balanced equation. I can see 2 to 1, it's half. So this will be, the change there will be 0,6. And now to find the ratio of 2 to 3, I can go to 1 to 3. That's just 3 times more. So that will be 1,8. That is the change. So for this part here, in this change, that is where my ratio helps me a lot. Now, what did they also give me? They gave me the initial number of moles that I started with, 5 and 5. So I've started with 5 there and there. Now I can work out what is the number of moles at equilibrium. I started with 5, 0,6 moles reacted, so I still have 4,4 left at equilibrium. Started with 5H2, 1,8 reacted, so I will still have 3,2 moles left at equilibrium. And now they told me the volume is 5 cubic decimeters, so to work out the concentration is number of moles divided by volume. So I'm going to take that number of moles, 4,4 divided by 5, and that will work out at 0,88. And I do the same with the next one. That will give me 0,64, and I do the same with that one, and it's going to give me 0,24. Okay, so there I have my table completed, and now I can write down my Kc equation, which still looks like this. It's the products at the top, so it will be my NH3 concentration at the top, and that has got a 2 in front of it, so I will square that, and then I will have my N2, which will be to the power 1, and I will have my H2, which will be to the power 3, because it's got a coefficient of 3 in front of it. Right, now I substitute in the place of my NH3 is 0,24 to the power 2. Here at the bottom it will be 0,88 to the power 1 multiplied by 0,64 to the power 3. And do the math on your calculator, and the value is 0,25. And this value being less than 1 shows me that this equilibrium is far towards the left. That just means that the concentration of my reactants is high and the concentration of my products is actually quite low. Right, so that is question 9 completed, and again the table makes my life very, very easy. Okay, let's go to a slightly more difficult one, which is then question 8. Okay, in question 8 we have the following. They say combustion at air at high temperatures produces oxides of nitrogen, of which nitrogen dioxide is the most common. Natural sources of nitrogen dioxide include lighting and activity in soil bacteria. These natural sources are small compared to emission caused by human activity. I will read fast over information like this because I will come back to it if there's a question on the uses and where it comes from and the human impact and things like that. All right, I want to get to the values. In a certain reaction, now I'm here with the important stuff, 2 moles of NO2 and the unknown amount of N2O4 are sealed in a 2 cubic decimeter container. Can you see that is my initial number of moles? Okay, so if I go to my table for this equation there's my equation. The mole ratio is 2 to 1. Okay, and they said now to me that the initial number of moles is 2 moles of NO2. So I can put in a 2 there. But they say I have an unknown amount of N2O4. I will put in an X there. I did not start with 0 N2O4 like normally. Here I had both of them in there, but I don't know what is the amount, the number of moles of N2O4. So let's use an X. All right. Then let's see what else they give me. They give me the volume. Okay, so The volume, I will write it down here, that the volume is equal to 2 cubic decimeters. Okay, so now what else information do they give me? They tell me at equilibrium, it is found that the NO2 concentration, that concentration is 0.4. Okay, at equilibrium, it is 0.4. So they gave me this concentration. That one, it was given to me. All right, and then they say the equilibrium constant at this temperature is 2. So they give me the Kc value is equal to 2. And that is the information they give me. And now they ask me, calculate the initial number of moles N2O4 in the container. So they want me to calculate for X. All right, now if I know what is the concentration at equilibrium, then I can go and work out what is the number of moles at equilibrium of the N2O4, where I use this very same formula that I have here, and I know what is the volume. So it will be concentration multiplied by volume will give me number of moles. So what I will find here is then, I will get here 0.8. So it's 2 times 0.4 using that equation. My concentration is 0.4 and my volume is 2. It was given to me. Right. Now I can work out what was the number of moles used, how much have reacted. You will agree that I started with 2. After equilibrium, it was 0.8, so 1.2, the difference between the two. That is the number of moles that have reacted. Now I can work out what is the number of moles that have formed using my ratio. This have reacted, so 1.2 moles will deliver half of it. So that will be 0.6, and that I got from my ratio. That number of moles used, it always links to my ratio. Okay, important to remember. Now I can know I started with this. This number of moles have formed. So what is the number of moles at equilibrium? It will be X plus 0.6. Okay, normally we have a 0 there, and then these two will be the same. But now I started with a number of moles of N2O4. Now I can calculate what will be the concentration. The concentration will be X plus 0.6 over 2, because there's my equation. Number of moles, X plus 0.6, divided by volume, which was given as 2, and I have my concentration. Now the Kc value was given as 2, so I can say that will be equal to what? It will be equal to the concentration of the N2O4, and that will be to the power 1, because there's a coefficient of 1, and divided by the reactants, which is the concentration of the NO2, and that I will have to the power 2, because there's a coefficient of 2 in front of it. Okay, and now I can substitute, and I can say that 2 is equal to, and I will have there, I will have X plus 0.6 over 2, and then divided by 0.4, which I will square. And there I've substituted everything, and now it's calculator and mathematics, and I will multiply across with the 0.4, and then afterwards I will multiply across with the 2 again, and then I will take the 0.6 as minus 0.6 to the other side, and then I will end up with X is equal to 0.04 moles. Right, so that is the number of moles that I have started with there, 0.04, and then another 0.6 was produced from my initial number of moles of NO2. Okay, so that was a slightly more difficult question where I give you the Kc value and I want you to work out one of the values in my table. All right, then they ask me, the plunger is now pushed in, causing the pressure to increase. So I have a pressure increase. And when I have a pressure increased, sorry, there's the question. Plunger is now pushed into the container, causing the pressure of the glass to increase because the volume have decreased, so my pressure increased. Now, talking of pressure, I like to go back to my balanced equation. On the left-hand side, I have 2 moles of gas. On the right-hand side, I have 1 mole of gas. So now the question is, what will happen to the amount of nitrogen dioxide? Okay, there's my nitrogen dioxide, NO2, it's nitrogen dioxide, okay, and what will happen to it if I increase the pressure? The system will try to decrease the pressure. How? By favoring the reaction where less amounts of gas will form. So the forward reaction will be favored because there's less of gas that will form, and thus if the forward is favored, then what's going to happen with the amount of the NO2, the nitrogen dioxide? It will decrease. So my answer here is decrease. I'm looking for the word decrease there. All right, and then the last question is, use the Chatelier principle to explain this question. So first of all, what is the disturbing factor? The pressure was increased. Now you will say, according to Le Chatelier, the system will react as to decrease the pressure. How will it decrease the pressure? By favoring the reaction where less amount of gas will form, and that is the forward reaction that will be favored because less is formed there to the right, okay, and thus then results in less NO2 that will form because NO2 will now disappear and N2O4 will form as a product. Right, so that was 3 questions. That brings us to the end of chemical equilibrium, the 5 parts. I think you will have a very good overview of this whole topic, which is a standalone question on its own in the final paper, and I hope that this will really help you to understand this topic much better. Thank you.